So there are two main features of quantum mechanics that we want to make use of when designing quantum algorithms, and that is superpositions. So we want to be able to prepare qubits into superpositions of multiple configurations, and we already know how to do this. For example, we can use the Hadamard gate, which takes 0 into an equally weighted superposition of 0 and 1, and it does the same for the state 1. With the sign flipped on the second state. Now the second thing that we want to be able to do is something called quantum entanglement. And we've only hinted to this concept up until now, but in order to introduce it, we first have to talk about multiple qubit interactions. So we need some sort of logic gate that's going to act on multiple qubits at the same time. So at the very least, we need a 2-qubit gate. So let's consider a very simple idea of how we can transform the state of 2 qubits. And it comes in this idea of what's called a controlled knot. So a controlled knot gate is sort of just like a logical knot on the state of a bit or a qubit, but it's conditioned on the state of another qubit. So for example, we could have 2 qubits, Q1 and Q2, and the action of this controlled knot is to flip Q2 if Q1 is equal to 1, and do nothing if Q1 is equal to 0. So this is what we mean by controlled knot. Now let's think about how we can actually implement this as a unitary matrix, because all of the actions that we can make on our qubits have to be unitary. So we know how to work with 1-qubit gates up until now, since 1-qubit gates act on a 2-dimensional vector space. We know that they're going to be 2x2 matrices. But how about 2-qubit gates? Well, when we discussed tensor products in the last video, we found that the state of 2 qubits is a 4-dimensional vector. So a linear transformation that's going to act on the state of 2 qubits has to be a 4x4 unitary matrix. Now let's think about how we can accomplish this controlled knot action on the state of 2 qubits, which we just reminded ourselves is a 4-dimensional vector. So we'll have 4 amplitudes corresponding to each of the 4 computational basis states for 2 qubits. And now we want to think about how we can design this 4x4 unitary matrix that's going to act on this state. And let's first convince ourselves that when we do implement this, it'll be reversible, so that we can actually make it unitary. Now, let's imagine this C naught on the state Q1 tensor Q2. Now this can be rewritten like what we've done up here as Q1 tensor Q2 XORed with Q1. And you can work it out for yourself that this will have the same exact action as flipping Q2 on the condition that Q1 is 1 and doing nothing if Q1 is 0. Actually, that's quite easy to see. So if Q1 is 0, XORed with Q2, you just get back Q2, just by the rules of this XOR addition. And if Q1 is 1, and Q2 can either be in the state 0 or 1, what's going to happen is it's just going to flip. Because 1 XORed with 1 is 0, and 0 XORed with 1 is 1. So now let's see what happens if we apply this C0 gate twice in a row. And we'll find that it is indeed reversible, because the outcome of this is Q1 tensor Q2 XORed Q1, but then again XORed Q1. And anytime you XOR something with itself, you get back 0. and then Q2 XORed with 0 is just Q2. So it takes it back into its initial state, and this C0 transformation would indeed be reversible. Now let's see what the unitary matrix should look like in order to accomplish this. And in order to do that, let's first think about what these probability amplitudes represent. So this state over here can be rewritten, we'll call it psi. Psi is a linear superposition of the 4 computational basis states for 2 qubits. And it's easy to see what these probability amplitudes each correspond to. Now, how should our C0 gate act on this superposition? Well, firstly, we know that it should do nothing to these 2 probability amplitudes, to these 2 states, since the first qubit in both of these states is 0. However, for the second group of states, the first qubit is 1, so they should flip. 1, 0 should become 1, 1, and 1, 1 should become 1, 0. And what that means is these last 2 probability amplitudes should swap places with one another. So we have alpha 1, 1, alpha 1, 0. So now we just need to figure out how we're going to fill in these dots on this unitary matrix such that we permute these last 2, or we swap these last 2 probability amplitudes. And we can come to this conclusion relatively quickly by understanding that this row in the unitary matrix is going to correspond to the first element, the second row to the second element, the third to the third, and the fourth to the fourth. Now for the first 2 elements, we want 1s along the diagonal. We just want the identity. And we want 0s everywhere else, because nothing happens to the first 2 amplitudes, so we just want it to act like the identity, which is just 1s across the diagonal. But now, for this third row, we want a contribution from the 4th probability amplitude. So what we do is we put a 1 on the 4th position and 0s everywhere else, giving us this row. And then finally, for the 4th row, we want a 1 on the 3rd spot so that we can have alpha 1, 0 at the bottom. And just like that, we found a matrix that is both reversible and preserves the norm. As we can see here, the norm of the 2, which is just all of these probability amplitudes squared and then summed, is going to be the same in either case, because you're just flipping these terms around. You're not adding anything new. So if this was equal to 1 before, it'll equal to 1 after. And this is indeed a unitary matrix because of that. Now we can return to this idea of quantum entanglement. How are we going to entangle the state of 2 qubits? So let's imagine we have this state, which is, it's going to start out just in the 0 state, 0 tensor 0. And now what we want to do is we want to put just the first qubit into a superposition. So what I'm going to say is Hadamard tensor identity, which means Hadamard on the first qubit, nothing to the second. And when this acts on our state psi, we're going to get this equally weighted superposition of 0 and 1, tensor 0. And now, let me expand this just by distributing out the 0. The 0. We have 0 tensor 0 plus 1 tensor 0. Now what happens if we apply a C0 or controlled knot to this state? Well, it should do nothing here, but it should flip this 0, since in this term we have that the first qubit is 1. And this is going to give us the state 0, 0 plus 1 tensor 1. Now, this, in fact, is an entangled state. These two qubits, remember this is qubit 1, this is qubit 2, but this is also qubit 1, and this is also qubit 2. They happen to be entangled here. And it's subtly different from this state up here in terms of entanglement, because this state is not entangled. Now, the definition of entanglement is, or the definition of entanglement for a 2-qubit state is one that can't be written as a tensor product of 2 single-qubit states. So with that definition, it's easy to see that this state up here is not entangled, since we just wrote it up here as a tensor product of 2 single-qubit states, namely 0 and then this superposition of 0 and 1. But we can't repeat that process over here. Now imagine we were trying to factor this out into 2 single-qubit states. How would you go about this? Well, the obvious way is to look at, okay, let's look at qubit 1. We see over here it's in the state 0, and over here it's in the state 1. So qubit 1, we'd write it as the superposition of 0 and 1. But then we'd also have to do the same thing for qubit 2. And then we'll see that what happens if we take the tensor product? Well, we certainly don't recover this state up here, since we get these cross terms 0 and 1, and also 1, 0, which don't show up over here. And this is what makes this state unique. We'll call it state psi. This is what makes psi unique, and this is what makes it entangled. In some sense, these individual qubits have lost their individuality, and they no longer have a state that simply describes them. There isn't one qubit without the other. There's only the combined system. And this is what is meant by entanglement. It's a purely quantum mechanical effect, and it's what's going to make certain quantum algorithms extremely powerful. And we'll be looking at some of those in the next video. So thank you.